Look out into the night sky, and everything appears tranquil, static, and serene. Stars seem pinned against an endless dark canvas, motionless in the cosmic expanse. But this calm appearance is a grand illusion. In truth, nothing in our universe is standing still. Right now, as you read these words, you are traveling through space at a speed that defies human comprehension. Earth is spinning on its axis at roughly 1,000 miles per hour, while orbiting the Sun at 67,000 miles per hour. Our entire solar system is sweeping around the core of the Milky Way at roughly 500,000 miles per hour. Yet even that tremendous orbital dance is only a small fraction of our true speed. Our entire galaxy, along with Andromeda and dozens of smaller neighbours, is hurtling through the cosmic abyss at an astonishing rate of more than 1,300,000 miles per hour, or roughly 600 kilometers per second. For decades, astrophysicists were haunted by a fundamental question. What could possibly possess enough gravitational power to pull millions of star systems, billions of worlds, and entire galaxies across vast distances at such staggering velocities? The answer points toward a shadowy, colossal cosmic region buried behind the dense gas and dust of our own galactic disk. Astronomers call this mysterious mass concentration the Great Attractor. It is an unseen gravitational anchor drawing our entire local sector of space toward its hidden center. But what is this cosmic structure? Is it a giant black hole, a massive cluster of galaxies, or something far beyond our standard cosmological models? Today, we will explore how big the Great Attractor really is. We will examine the evidence gathered by modern astrophysics, peer through the obscured zone of our night sky, and measure the true scale of the cosmic leviathan pulling our galaxy through the void. To truly grasp how fast we are moving and why the Great Attractor exerts such a powerful influence, we must first answer a fundamental question. Compared to what are we moving? In daily life, motion is simple to measure because we have fixed references. A car moves relative to the asphalt beneath its tyres. An airplane travels relative to the atmosphere or the land below. But in the vastness of deep space, where there are no road signs or stationary physical markers, establishing a true frame of rest proved to be one of the greatest challenges in 20th century astrophysics. For a long time, astronomers relied on the Hubble flow, which describes the uniform expansion of space itself. Ever since Edwin Hubble demonstrated that distant galaxies are moving away from us, scientists understood that the fabric of space is stretching. According to this general cosmological expansion, every galaxy should recede from every other galaxy at a speed proportional to its distance. If the universe were expanding perfectly uniformly without any local distortions, a galaxy twice as far from us as another would appear to recede twice as fast. In such a hypothetical universe, there would be no preferred direction of movement other than the smooth, outward stretching of space. However, reality is far more complex and dynamic. The universe is not a perfectly smooth fluid, it is clumpy. Matter is clumped into stars, galaxies, galaxy clusters, and massive cosmic filaments, leaving vast empty regions known as cosmic voids between them. Because mass exerts gravity, these local concentrations of matter create localized gravitational fields that pull nearby objects toward them. This creates what astronomers call peculiar velocity. A galaxy's total motion through space is therefore a combination of two distinct components. Its Hubble velocity, which is the speed at which it recedes due strictly to the expansion of space, and its peculiar velocity, which is its individual motion caused by the gravitational pull of nearby mass concentrations. To isolate our own peculiar velocity, the actual speed at which the Milky Way is travelling through the cosmos, astrophysicists needed an ultimate cosmic benchmark. They found it in the cosmic microwave background radiation, often abbreviated as the cosmic background radiation. This background radiation is the ancient remnant thermal energy left over from the Big Bang, dating back to a time when the universe was merely 380,000 years old. It permeates every cubic inch of space in all directions, forming a nearly uniform ocean of microwave photons with an average temperature of approximately 2.725 Kelvin above absolute zero. Because this radiation fills the entire observable cosmos, It serves as the ultimate rest frame for the universe. If our solar system and galaxy were at rest relative to this cosmic background, the radiation arriving at our sensors from every direction in space would have the exact same temperature and wavelength. However, when sensitive spaceborne detectors like the Cosmic Background Explorer satellite, followed later by the Wilkinson Microwave Anisotropy Probe and the Planck Space Observatory, mapped this ancient light with extreme precision, they discovered a striking pattern known as the cosmic dipole anisotropy. The cosmic dipole anisotropy reveals a distinct thermal asymmetry across the sky. In one particular direction, toward the constellations of Crater and Leo, the cosmic microwave background radiation appears slightly warmer than average by approximately 3.35 millikelvin. In the exact opposite direction, the radiation appears slightly colder by the same minute fraction. This subtle temperature variation is caused by the Doppler effect acting on light photons. As our solar system moves through the background radiation, the photons ahead of us are shifted toward higher frequencies and shorter wavelengths, causing them to appear hotter. Conversely, the photons behind us are shifted toward lower frequencies and longer wavelengths, causing them to appear cooler. By measuring the precise magnitude of this Doppler shift across the sky, astrophysicists calculated our net velocity with incredible precision. The data indicate that our solar system, along with the Milky Way and the entire local group of galaxies, is moving relative to the cosmic microwave background rest frame at approximately 627 kilometers per second, which translates to nearly 1,400,000 miles per hour. This direction points toward a specific patch of sky near the constellation Centaurus. This discovery sent shockwaves through the scientific community. A small fraction of this motion could be explained by the mutual gravitational attraction between our Milky Way galaxy and our massive neighbour, the Andromeda Galaxy. That local interaction accounts for only a minor portion of our total speed. Even when taking into account the combined gravitational pull of all the nearby galaxies in our immediate neighbourhood, what we refer to as the local group, the total calculated gravitational force was nowhere near strong enough to accelerate our galaxy to a velocity of more than 600 kilometers per second. Standard cosmological models, based purely on uniform cosmic expansion, predicted that peculiar velocities should average out over large scales, leaving galaxies to drift smoothly with the expanding fabric of space. Instead, observational data clearly demonstrated that a massive region of space, spanning hundreds of millions of light-years, was engaged in a coherent bulk motion. Entire groups and clusters of galaxies were moving in unison, like a vast cosmic river flowing toward an unseen ocean. Scientists realized that somewhere in the direction of Centaurus, hidden behind billions of light-years of space, there must exist an extraordinary concentration of mass. This immense mass had to possess enough gravitational pull to overcome the general expansion of the universe across local scales, dragging our galaxy and thousands of others along with it. This realization marked the official beginning of the search for the monster behind the motion. Researchers around the globe began pointing their telescopes toward the coordinates dictated by the cosmic dipole, attempting to identify the hidden gravitational anchor responsible for this colossal spatial drift. Yet, when optical astronomers looked toward those coordinates, they encountered an insurmountable wall of darkness, concealing the very structure they sought to understand. When astronomers first calculated the trajectory of our galaxy's peculiar velocity, they pointed their finest optical telescopes directly toward the sky coordinates where the gravitational source should reside. What they found instead was an agonizing blank space in our cosmic mapping. The mysterious origin of this massive gravitational pull happened to lie almost directly behind the plane of our own galaxy. This obscured region of the night sky is known to astrophysicists as the Zone of Avoidance. The Zone of Avoidance is not a literal empty void in the universe. Rather, it is a blind spot created by our perspective from inside the Milky Way. Our planet resides within the flattened disk of a spiral galaxy containing hundreds of billions of stars, vast nebulae, and uncountable trillions of tons of interstellar gas and cosmic dust. When we look up or down, out of the galactic plane, our view into deep space is relatively clear. allowing optical telescopes to capture faint light from galaxies billions of light-years away. However, when we attempt to look directly along the plane of the galactic disk, our line of sight must pass through tens of thousands of light-years of dense interstellar material. Cosmic dust consists of tiny microscopic grains of carbon, silicon, and icy compounds scattered throughout the interstellar medium. Although these particles are individually minuscule, collectively they act as an impenetrable fog bank across astronomical distances. This dust preferentially scatters and absorbs short wavelengths of light, such as ultraviolet and visible light, through a process known as interstellar extinction. As a result, the optical light emitted by distant galaxies hiding behind the Milky Way's disk is dimmed by factors of thousands or even millions. For decades, traditional optical astronomy was rendered completely blind across approximately 20% of the night sky, leaving a massive gap in our maps of the surrounding universe. For generations of astronomers, this cosmic curtain created an infuriating paradox. The most significant gravitational driver in our local region of the universe was actively pulling us toward itself, yet the very galaxy we inhabit was blocking our ability to see what it was. To solve this mystery, scientists had to abandon visible light entirely and develop innovative observational techniques capable of penetrating the thick shroud of dust and gas. The first major breakthrough came with the advancement of infrared astronomy. Unlike visible light, which has short wavelengths that easily collide with dust grains, infrared radiation possesses longer wavelengths that can bend around small dust particles with minimal interference. By deploying infrared detectors on ground-based observatories and launching specialized space telescopes, astronomers began to pierce the outer layers of the Zone of Avoidance. Survey projects, such as the 2-micron all-sky survey, mapped millions of previously hidden stars and revealed the faint silhouettes of distant galaxies glowing through the cosmic haze. Infrared imaging showed that the universe behind the galactic plane was far from empty. It was teeming with dense, cosmic structures that had remained unnoticed for centuries. However, while infrared light could slice through moderate concentrations of dust, the densest central core of the Milky Way remained extremely difficult to penetrate. To look through the absolute thickest regions of interstellar gas, radio astronomers turned to neutral hydrogen spectral observations. Hydrogen is the most abundant element in the universe, and cold, neutral hydrogen gas naturally emits radio waves at a precise wavelength of 21 centimeters. Radio waves possess vastly longer wavelengths than infrared light, allowing them to pass through interstellar dust clouds completely unimpeded, as if the dust were not even there. Using massive radio telescopes, such as the iconic Parkes Observatory in Australia, astronomers conducted systematic surveys of the 21-centimeter neutral hydrogen line across the Zone of Avoidance. By measuring the slight shifts in these radio signals caused by the Doppler effect, researchers could not only detect hidden galaxies, but also calculate their distances and orbital speeds. These radio observations mapped thousands of unknown galaxies scattered across the obscured zone, effectively drawing the first reliable structural outlines of the hidden universe. While radio waves revealed the cold hydrogen gas of distant galaxies, scientists still needed a way to locate the most massive structures hidden in the shadows. Galaxy clusters, the largest gravitationally bound structures in the cosmos, contain vast reservoirs of extremely hot, ionized gas suspended between their individual galaxies. This intracluster medium reaches temperatures of tens of millions of degrees, causing it to emit powerful, energetic X-rays. Because cosmic dust absorbs light primarily at optical wavelengths and does not effectively block high-energy X-rays, X-ray space observatories provided the ultimate tool for pinpointing massive gravitational centers behind the Milky Way. Missions such as the ROSAT satellite, followed by advanced space observatories like Chandra and XMM Newton, began surveying the Zone of Avoidance in the X-ray spectrum. The cluster in and around the Zone of Avoidance project, known as SIZA, specifically targeted these high-energy X-ray signatures to hunt for massive galaxy clusters concealed behind our galactic core. The results of these multi-wavelength campaigns transformed our understanding of the local universe. By combining radio waves to trace cold hydrogen gas, infrared light to capture the faint glow of older star systems, and X-ray observations to identify hot cluster gas, astronomers finally peeled back the dark veil of the Milky Way. Where once there was only an impenetrable black void, a dramatic cosmic landscape emerged. Behind the dense star fields of the constellation Norma, deep within the heart of the Zone of Avoidance, detectors revealed a dense concentration of thousands of galaxies bound together by gravity. Astronomers had finally located the central core of the anomaly. The long-sought source of our galaxy's mysterious acceleration was no longer an invisible ghost. It was a physical structure of astonishing proportion and mass. Yet as the first clear images and data from these multi-spectrum surveys were analysed, researchers realised that identifying the location of this gravitational giant was only the first step. Understanding its true nature, measuring its absolute mass and determining whether it alone possessed enough power to drag our entire cosmic neighbourhood across space would present a whole new set of scientific challenges. Once multi-wavelength astronomical observations successfully breached the dusty curtain of the Zone of Avoidance, scientists could finally analyse the true structural nature of the Great Attractor. Popular science lore had often envisioned this mysterious anomaly as a single, terrifying superobject, perhaps a supermassive black hole of unfathomable proportions, or a dense, primordial monster consuming everything in its path. However, high-energy astrophysics revealed a far more complex and majestic reality. The Great Attractor is not a single celestial body. It is a diffuse, extraordinary mass concentration spanning tens of millions of light-years, consisting of countless galaxies, dark matter halos, and superheated intracluster gas. At the heart of this gravitational anomaly lies a massive cluster of galaxies, officially designated as Abell 3627, more commonly referred to as the Norma Cluster. Situated approximately 200 million light-years away from Earth, in the direction of the constellation Norma, this cluster serves as the primary focal core of the Great Attractor region. Before X-ray and radio surveys penetrated the galactic plane, astronomers had severely underestimated the scale of Abell 3627 due to heavy dust extinction. Once X-ray space observatories detected the brilliant thermal glow of its hot intracluster medium, researchers recognized that the Norma Cluster is an absolute titan among cosmic structures. The Norma Cluster contains thousands of individual galaxies tightly bound together by their mutual gravitational attraction. At its center sit giant elliptical galaxies that have grown through billions of years of galactic cannibalism, merging with smaller neighbors and accumulating immense mass. The overall density of galaxies within Abell 3627 is remarkably high compared to typical regions of space, indicating an exceptionally deep gravitational potential well. However, Abell 3627 is not acting in total isolation. It is surrounded by several other prominent galaxy clusters, including the Centaurus cluster, the Hydra cluster, and the Pavo-Indus Supercluster, all interconnected through vast filaments of cosmic matter. When astrophysicists calculated the total gravitational influence required to account for the peculiar velocities observed across our sector of space, they estimated the overall mass of the Great Attractor region to be on the order of 10 to the power of 15 solar masses, or approximately 1 quadrillion times the mass of our Sun. In expanded numerical terms, this represents roughly 10 million billion solar masses. To put this into perspective, a single solar mass equals the total mass of our Sun, which itself outweighs planet Earth by more than 300,000 times. An accumulation of mass equivalent to 10 million billion suns represents a gravitational force capable of warping the trajectories of entire cosmic neighborhoods. Despite these staggering numbers, scientists maintain a strict degree of empirical caution when discussing the precise mass estimates of the Great Attractor. Calculating the exact mass of a structure buried deep within the Zone of Avoidance remains an exceptionally delicate scientific task, subject to notable observational uncertainties. Because interstellar dust and gas still partially obscure our view, measuring the complete light output, velocity dispersions, and gas temperatures across the entire region requires sophisticated modeling and indirect extrapolation. Furthermore, visible matter, The stars, dust, and gas that emit electromagnetic radiation accounts for only a small fraction of the total mass within the Great Attractor region. The vast majority of its calculated mass exists in the form of dark matter, an elusive, non-luminous substance that does not interact with light but exerts immense gravitational influence. Astronomers infer the presence and distribution of this dark matter by analyzing the orbital speeds of galaxies moving within the cluster and by measuring how the cluster's mass bends light from even more distant background objects through gravitational lensing. Because our maps of the Zone of Avoidance are continuously being updated as observational technology improves, published mass estimates for the Great Attractor vary depending on where scientists draw its spatial boundaries. If one measures strictly the core of the Norma Cluster, the mass is significant but limited. If one includes the surrounding filaments, satellite clusters, and associated dark matter halos that move coherently within the local gravitational basin, the total mass scales up dramatically toward the 10 million billion solar mass threshold. Current cosmological models indicate that the Great Attractor represents a major density fluctuation that originated in the very early universe. Shortly after the Big Bang, minute quantum fluctuations created tiny variations in the distribution of matter. Over billions of years, gravity acted as an amplifier, pulling matter out of lower density regions and piling it into high-density nodes. The Great Attractor is one such high-density node, a massive cosmic intersection where gravity has been pulling material together for over 13 billion years. Yet, as astronomers refined their measurements of the Norma Cluster and its surrounding structures, a profound scientific puzzle emerged. When theorists plugged the revised mass estimates of the Great Attractor into gravitational dynamics equations, the numbers revealed an unsettling discrepancy. The mass of the Norma Cluster and its associated local structures, while colossal, was simply not large enough to fully explain the rapid 600 km/s peculiar velocity of our Milky Way and the local group. According to classical Newtonian gravity and general relativity, a mass concentration of 10 million billion solar masses at a distance of 200 million light-years should exert a powerful pull, but it accounts for only roughly 40 to 50% of our total observed peculiar motion. The gravitational tug-of-war pulling our galaxy through space was missing nearly half of its required force. This critical realization forced astrophysicists to reconsider their models of the local universe. Either the mass of the Great Attractor was still heavily underestimated due to unseen dark matter hidden in the deepest zones of the Milky Way's shadow, or the Great Attractor itself was merely a participant in a much larger cosmic drama. The search for the missing mass suggested that our galaxy was not merely falling toward a single, isolated cluster, but was instead flowing along a vast, overarching cosmic current driven by structures stretching far beyond the original boundaries of the Great Attractor anomaly. For decades, astronomers mapped the local universe using rigid spatial boundaries based purely on visual proximity. Under this traditional paradigm, our Milky Way galaxy was categorized as a member of the local group, a small cluster of roughly 80 galaxies dominated by ourselves and the Andromeda Galaxy. The local group was considered an outlying fringe component of the larger Virgo Supercluster, a massive collection of thousands of galaxies centered on the dense Virgo cluster roughly 55 million light-years away. However, this traditional visual mapping suffered from a fundamental flaw. It looked at where galaxies were physically located in static three-dimensional space, rather than analyzing how they were actually moving under the dynamic influence of gravity. Just as political maps drawn on land often fail to reflect the natural flow of rivers and drainage basins, static galaxy maps failed to reveal the true cosmic currents shaping our universe. In 2014, a breakthrough research team led by astronomer Brent Tully at the University of Hawaii revolutionized our understanding of cosmic geography. By developing a sophisticated methodology that mapped the peculiar velocities of thousands of galaxies across our local universe, the team created a dynamic velocity field map. Instead of merely plotting cosmic coordinates, they tracked the direction and speed of actual galactic motion after subtracting the uniform expansion of space. This dynamic approach revealed a completely new picture of cosmic structure. the researchers discovered that vast regions of space function precisely like terrestrial watershed basins. On Earth, rain falling on a mountain range flows down individual streams into rivers, eventually draining into a single ocean basin defined by topographical watersheds. Similarly, in the cosmos, galaxies flow along invisible gravitational pathways defined by the distribution of mass. Using this velocity flow framework, the team mapped the true boundaries of our cosmic home and unveiled a staggering new structure, the Laniakea Supercluster. The name Laniakea, derived from Hawaiian, translates to immense heaven or immeasurable sky, an apt description for a cosmic structure spanning more than 500 million light-years across and containing the mass of roughly 100 quadrillion suns, encompassing over 100,000 individual galaxies. The discovery of Laniakea fundamentally redefined Earth's address in the cosmos. Our Milky Way, along with the entire local group and the previously independent Virgo supercluster, was revealed to be merely a small suburban branch within this vast, interconnected cosmic continent. What astronomers had previously classified as standalone superclusters were shown to be interconnected tributaries flowing within a single unified gravitational watershed. At the very heart of this vast Laniakea watershed lies the Great Attractor. Within the structural geography of Laniakea, the Great Attractor acts as the ultimate gravitational valley, the central low point of the cosmic terrain toward which all internal streams of matter flow. To visualize this phenomenon, imagine a large, flexible rubber sheet pulled down in the center to form a deep funnel. If you scatter marbles across different regions of the sheet, each marble will roll along the local slope toward the central depression. In Laniakea, the galaxies are the marbles, and the deep gravitational depression created by the Norma Cluster and its surrounding mass concentrations represents the focal bottom of the basin. Galaxies residing on one side of Laniakea are streaming inward toward the Great Attractor from one direction, while galaxies on the opposite boundary, hundreds of millions of light-years away, are falling inward from the reverse direction. Every galaxy contained within the outer boundary of Laniakea shares this common dynamical destiny. Their peculiar velocities are aligned along streamlines that vector directly toward the core region of the Great Attractor. The boundary of Laniakea is explicitly defined by the surface where these gravitational currents diverge. Outside the perimeter of Laniakea, neighboring galaxies are captured by adjacent gravitational watersheds and stream toward entirely different cosmic centers, such as the Perseus-Pisces supercluster. The boundary of Laniakea is therefore not a physical wall or a visible barrier, but a strict dynamical divide, a cosmic watershed line where a galaxy placed on one side flows toward the Great Attractor, while a galaxy placed mere light-years away on the other side flows away into a neighboring domain. This flow-based mapping provided an elegant solution to a long-standing cosmological question. Why does the Great Attractor exert such a coherent pull over such immense distances? The answer is that the Great Attractor is not pulling galaxies through isolated brute force attraction across empty space. Rather, it represents the primary gravitational focal point of an entire integrated cosmic ecosystem. The vast filaments of dark matter and intergalactic gas that construct the framework of Laniakea act as gravitational channels, guiding galaxies along predetermined cosmic highways toward the central valley. By viewing the Great Attractor as the gravitational heart of Laniakea, astrophysicists gained a far clearer understanding of our galaxy's place in the universe. We are not drifting randomly through a featureless void, nor are we being drawn toward an isolated cosmic anomaly by sheer chance. The Milky Way is an active participant in a vast, organized cosmic current, sliding down the gravitational slopes of Laniakea toward its central core at hundreds of kilometers per second. Yet, even as the mapping of Laniakea provided an extraordinary framework for understanding our local cosmic geography, it also highlighted a deeper, more complex cosmological puzzle. When astronomers precisely measured the velocity vectors of galaxies flowing toward the center of Laniakea, they noticed that the entire Laniakea supercluster itself, including the Great Attractor at its core, appeared to be sliding toward an even more distant point in space. The gravitational valley of Laniakea, colossal as it is, turned out to be situated on a larger incline. This realization suggested that while the Great Attractor defines our immediate local basin, there are vast cosmic structures operating on scales far exceeding Laniakea, exerting gravitational forces that reach across billions of light-years. To understand the complete motion of our galaxy, scientists had to look beyond the boundaries of our celestial home and peer even deeper into the cosmic web. As cosmic velocity maps grew increasingly sophisticated throughout the late 20th and early 21st centuries, astrophysicists were confronted with a stubborn mathematical discrepancy. The total measured mass of the Great Attractor, even when accounting for the full extent of the Norma Cluster and the vast dark matter-dominated filaments of the Laniakea Supercluster, simply could not generate enough gravitational acceleration to account for the Milky Way's observed peculiar velocity of over 600 kilometers per second relative to the cosmic microwave background. According to precise calculations based on Einstein's theory of general relativity, the combined mass concentration located within the central region of the Great Attractor should account for only a fraction, roughly 40 to 50%, of our total peculiar velocity. The remaining acceleration required an additional source of momentum. For many years, scientists hypothesized that this missing force was located entirely ahead of us, buried even deeper behind the Zone of Avoidance in undiscovered superclusters. However, a revolutionary alternative hypothesis emerged that turned conventional thinking upside down. What if our high-speed drift through space was not caused solely by a pull from in front, but also by a push from behind? In 2017, a team of international astrophysicists, led by Yehuda Hoffman at the Hebrew University of Jerusalem, published a landmark study that introduced a groundbreaking concept to observational cosmology: the Dipole Repeller. To understand how a region of space can appear to exert a repulsive force without invoking exotic anti-gravity physics, one must examine how mass density operates on cosmic scales. In the standard model of cosmology, the universe on large scales is governed by gravity, which is exclusively an attractive force. Matter attracts matter. However, the distribution of matter across the universe is not perfectly uniform. It forms a complex structure known as the cosmic web, composed of dense nodes of galaxy clusters connected by long filaments, separated by vast, nearly empty regions called cosmic voids. In a perfectly uniform universe, a galaxy experiences equal gravitational pull from all directions, resulting in zero net acceleration. But if you place a galaxy between a region of extraordinarily high density on one side and a region of extreme low density on the other side, a distinct dynamical imbalance occurs. The high-density region exerts a strong gravitational pull, drawing the galaxy toward itself. Simultaneously, the low-density region lacks the average mass necessary to pull back against that attraction. Because space is expanding, a region with a severe deficit of matter, an underdensity, exerts far less gravitational attraction than the cosmic average. Relative to the surrounding medium, this lack of attraction causes surrounding matter to stream away from the void toward areas of higher density. To an observer inside a moving galaxy, the void effectively behaves as if it were pushing matter away, creating a repulsive dynamical effect. By constructing three-dimensional velocity field maps using the cosmic flows of thousands of galaxies, Hoffman and his colleagues identified an immense, underdense cosmic void located directly behind the Milky Way, relative to the direction of our motion toward the Great Attractor. This vast, nearly empty cavern of space was designated as the Dipole Repeller. The Dipole Repeller is an astonishing structure, or more accurately, an extraordinary absence of structure. Spanning hundreds of millions of light-years across, this immense cosmic void contains extraordinarily few galaxies and a near-total absence of dark matter relative to the cosmic average density. Situated approximately 220 million light-years from Earth in the direction of the constellation Indus, the Dipole Repeller lies almost directly opposite our trajectory toward the Great Attractor and the Shapley Concentration. This opposing alignment creates a classical dipole configuration, a push-pull dynamic that neatly resolves the missing velocity problem. The extreme underdensity of the Dipole Repeller effectively pushes the Milky Way and our neighboring galaxies away from its center, while the extreme overdensity of the Great Attractor and its surrounding structures pulls us toward them. Rather than being acted upon by a single isolated source of gravity, our galaxy is positioned on a cosmic slide between an expansive void and a massive gravitational wall. The repulsive flow generated by the dipole repeller provides the additional momentum necessary to match the 600 km/s velocity vector measured by cosmic microwave background dipole observations. To visualize this mechanism, picture a crowded room where people represent galaxies and mass concentrations. If a large crowd gathers tightly in one corner of the room, they create a dense center of attraction, drawing nearby individuals toward them. If, at the same time, a vast empty space suddenly opens up in the opposite corner because everyone has cleared out, an individual standing in the middle will naturally feel pulled toward the crowd and moved away from the empty space. The physical movement away from the empty area is not caused by an invisible wall pushing from behind, but by the net absence of resistance and gravitational equilibrium. The hypothesis of the dipole repeller marked a profound shift in how astrophysicists model cosmic dynamics. It demonstrated that cosmic voids are not merely passive empty spaces between galaxies. They are active dynamical drivers that shape the large-scale architecture of the universe. The trajectories of entire superclusters are dictated as much by the empty regions they avoid as by the massive structures they seek. Furthermore, recent cosmic flow analyses suggest that the dipole repeller may not be unique. Other underdense regions, such as the cold spot repeller, may also be contributing to the complex, large-scale motions observed throughout the observable universe. These vast voids act as cosmic engines of clearance, evacuating matter over billions of years and channeling it into the surrounding filaments and nodes of the cosmic web. This dual push-pull model provides a remarkably elegant framework for understanding our cosmic journey, yet it also emphasizes the need for scientific caution. Measuring the exact boundaries, mass deficits, and repulsive influence of an underdense void presents significant observational challenges. Because voids contain very few luminous galaxies, astronomers must map them indirectly by observing how the surrounding galaxies move away from their empty centers. As researchers refined these dynamic flow models, it became increasingly clear that our cosmic trajectory is shaped by an intricate interplay of forces operating across multiple scales. The dipole repeller provides an essential push from behind, and the Great Attractor offers a localized pull ahead. However, as scientists tracked these velocity vectors even farther across the cosmic expanse, they discovered that both the dipole repeller and the Great Attractor are themselves embedded within an even larger, more dominant gravitational landscape that reaches far beyond the boundaries of our local supercluster. While the mapping of the Laniakea Supercluster and the discovery of the dipole repeller provided a crucial framework for understanding our immediate neighborhood, astronomers knew the cosmic journey did not end there. As deep space mapping techniques matured and high-energy instruments scanned beyond the local velocity fields, a startling realization emerged. The Great Attractor itself, along with the entirety of Laniakea, is not a stationary destination, it is moving. Beyond the outer perimeter of Laniakea, situated hundreds of millions of light-years further out in the cosmic abyss, lie megastructures of truly unimaginable proportions. The most formidable of these cosmic giants is the Shapley Supercluster, officially designated by astronomers as the Shapley Concentration. Named after the pioneering American astronomer Harlow Shapley, who first noted its faint signature in the 1930s, this structure represents the most massive concentration of matter in the known universe, within a distance of 1 billion light-years from Earth. Located approximately 650 million light-years away, more than 3 times as distant as the Great Attractor, the Shapley Concentration is a sprawling cosmic leviathan. While a typical galaxy cluster contains dozens to hundreds of bright galaxies, the Shapley Concentration encompasses over 25 individual rich galaxy clusters, including massive systems such as Able 3558 and Able 3562, bound together in a dense gravitational web. The scale of the Shapley Concentration defies easy visualization. It spans hundreds of millions of light-years across and possesses a total mass estimated to be roughly 10 to the power of 16 solar masses, equivalent to 10 quadrillion suns, or tens of thousands of times the mass of the entire Milky Way. This immense accumulation of baryonic matter and dark matter creates a gravitational potential well so vast and deep that it exerts a measurable pull across billions of cubic light-years of space. Astronomical velocity surveys conducted over recent years have demonstrated that the Great Attractor and the Shapley Concentration are intimately connected. In fact, current cosmological models suggest that the Great Attractor is acting as an intermediate cosmic stepping stone or gravitational relay point. The Milky Way, the local group, and the surrounding galaxies of Laniakea are falling toward the Great Attractor. But the Great Attractor itself, along with the central core of Laniakea, is being relentlessly drawn toward the far greater gravitational abyss of the Shapley Concentration. This hierarchical structure reveals that the Great Attractor, while immense on the scale of our local cluster, is merely a subordinate feature within a much larger cosmic stream. The entire Laniakea Supercluster is effectively moving along an overarching velocity path dictated by the massive gravitational field of Shapley. However, the Shapley Concentration is not the only megastructure shaping this grand cosmic current. In 2016, an international team of astrophysicists using the Southern African Large Telescope and the Parkes Radio Telescope announced the discovery of another monumental structure hidden behind the southern plane of the Zone of Avoidance, the Vela Supercluster. Situated approximately 800 million light-years from Earth, the Vela Supercluster had remained concealed for centuries due to extreme interstellar extinction caused by the thick dust lanes of the Milky Way. When multi-wavelength radio and optical spectroscopy finally mapped its extent, researchers discovered a massive, previously unmapped concentration of galaxy clusters spanning an enormous area of sky. Initial velocity field calculations indicate that the gravitational influence of the Vela supercluster is far from negligible. Because of its colossal mass, Vela contributes a significant gravitational pull that helps steer the large-scale bulk flow of galaxies in our sector of the universe. The discovery of Vela demonstrated that our understanding of cosmic velocity drivers is still evolving, as hidden mass concentrations buried deep within the Zone of Avoidance continue to be revealed by modern instruments. The combined presence of the Shapley Concentration, the Vela Supercluster, the Great Attractor, and the Dipole Repeller paints a breathtaking picture of the large-scale architecture of the cosmos. We inhabit a universe defined by nested hierarchies of gravity. Small systems, like our solar system, orbit within galaxies. Galaxies cluster into local groups. Local groups flow along the channels of superclusters like Laniakea toward regional gravitational centers like the Great Attractor. And these regional centers are in turn pulled across vast cosmic gulfs toward massive cosmic nodes like Shapley and Vela. Scientific rigor requires that we view these megastructures through a lens of observational caution. At distances exceeding 600 million light-years, mapping the precise boundaries, dark matter distribution, and exact mass ratios of structures like Shapley and Vela involves complex statistical modeling. Distinguishing between galaxies that are actively bound to these superclusters and those that are merely passing through due to background cosmological expansion remains an ongoing challenge in observational astronomy. Nevertheless, the overarching physical narrative is clear. The Great Attractor is not the ultimate destination of our galaxy, nor is it the largest object in the universe. It is a local gravitational focal point, a dramatic, high-density node within a vast, continuous network of cosmic filaments stretching across the observable universe. As we zoom out to encompass these colossal scales, a fascinating paradox emerges. We see a universe dominated by titanic gravitational forces, pulling mass together into immense structures spanning hundreds of millions of light-years. Yet, at the exact same time, a competing force operates across the cosmological stage, a force that threatens to rewrite the ultimate fate of the Great Attractor, Shapley, Vela, and our own galaxy. To understand whether our long journey through space will ever reach its destination, we must look beyond gravity itself and examine the mysterious, invisible framework governing the ultimate expansion of the universe. To truly comprehend the mechanics behind the Great Attractor and the grand architectural framework of the cosmos, we must look beyond the visible light emitted by stars, nebulae, and shining galaxies. The luminous matter that populates our night sky Everything built from atoms, protons, electrons, and neutrons represents only a tiny fraction of the total mass-energy budget of the universe. The vast structural web connecting Laniakea, the Norma Cluster, the Shapley Concentration, and the surrounding cosmic voids is governed almost entirely by two invisible, mysterious components: dark matter and dark energy. Dark matter serves as the invisible framework of cosmic structure. Although dark matter does not absorb, reflect, or emit electromagnetic radiation, making it completely invisible to conventional telescopes across all wavelengths, its presence is unmistakably revealed by its gravitational influence. When astrophysicists analyze the internal orbital speeds of galaxies within the Norma Cluster, or calculate the total gravitational pulling power required to drive our 600 km per second peculiar velocity, the visible mass of stars and intergalactic gas falls severely short. Baryonic matter accounts for less than 15% of the total matter content in these massive structures. The remaining 85% consists of cold, dark matter. Huge diffuse halos of dark matter encompass galaxy clusters, providing the essential gravitational glue that prevents rapidly moving galaxies from flying apart into the void. In the context of the Great Attractor, dark matter acts as the primary builder. In the early universe, dark matter collapsed under its own gravity long before ordinary matter could, forming deep gravitational wells. Ordinary gas and dust then fell into these pre-existing dark matter valleys, eventually igniting into stars and assembling the galaxies we observe today. Without the massive scaffolding of dark matter, the Great Attractor simply would not possess the gravitational density required to pull surrounding galaxies across hundreds of millions of light-years. Yet, while dark matter acts as the cosmic glue binding matter together into dense clusters, an even more dominant force governs the overarching fate of the universe on global scales: dark energy. Discovered in the late 1990s through observations of distant Type 1a supernovae, dark energy is a mysterious property of space itself that exerts a negative pressure, driving the accelerated expansion of the universe. While gravity pulls matter together over localized distances, dark energy stretches the very fabric of space apart on cosmic scales. This interplay between the attractive force of gravity and the repulsive expansion driven by dark energy creates a profound cosmological paradox regarding our galaxy's ultimate journey toward the Great Attractor. Because the Great Attractor exerts such a powerful gravitational attraction, one might naturally assume that our Milky Way galaxy, along with the local group and the thousands of galaxies streaming along the Laniakea watershed, will eventually collide with the Norma Cluster in the distant future, merging into an enormous cosmic megastructure. However, rigorous cosmological calculations indicate that this dramatic collision will never happen. The reason lies in the relentless, accelerating expansion driven by dark energy. While the gravitational pull of the Great Attractor is remarkably strong across local distances, the space separating our galaxy from the core of the Norma Cluster, a distance of roughly 200 million light-years, is expanding continuously. On large cosmological scales, dark energy dominates over gravitational attraction. As time progresses, the rate at which dark energy expands the space between Laniakea's outer regions and its central core will gradually outpace the speed at which gravity can draw galaxies inward. Although our galaxy is currently moving toward the Great Attractor at hundreds of kilometers per second through local space, space itself is expanding at an ever-increasing rate across that intervening distance. Consequently, while our peculiar velocity vectors currently point toward the core of the Great Attractor, we will never actually arrive at its gravitational center. Instead, as dark energy continues to accelerate cosmic expansion over tens of billions of years, the overarching boundaries of Laniakea will eventually stretch, fragment, and break apart. Distant structures like the Shapley Concentration and the Unveiling Supercluster will be carried away beyond our cosmic horizon at speeds exceeding the speed of light, disappearing forever from our observable sky. Even the central core of the Great Attractor itself will slowly recede from our perspective, carried away by the expanding ocean of space. The local gravitational bound structures, such as our Milky Way and the Andromeda Galaxy, will complete their own local merge, forming a single giant elliptical galaxy. But our long-distance journey toward the Great Attractor will be permanently severed. Science teaches us to approach these cosmic predictions with appropriate empirical hedging. Our understanding of dark matter and dark energy remains based on their observed cosmological effects, rather than direct laboratory detection. The precise fate of Laniakea depends heavily on the exact equation of state of dark energy, whether it remains a constant cosmological factor or evolves dynamically over cosmic time. Current cosmological models based on the standard lambda cold dark matter model strongly indicate that dark energy will remain constant, ensuring the ultimate isolation of galactic groups. This realization transforms our perspective on the Great Attractor. It is not an inevitable final destination or a terrifying cosmic trap that will swallow our galaxy. Instead, it represents a majestic, temporary alignment of cosmic currents, a testament to the power of gravity building immense structures across billions of years, set against the backdrop of an expanding universe that will ultimately pull the cosmic web apart. As we zoom out from the dense core of the Norma Cluster, past the sweeping boundaries of the Laniakea Supercluster, and into the seemingly infinite expanse of the cosmic web, the true nature of the Great Attractor comes into sharp focus. It is undeniably a behemoth of cosmic proportions, a massive gravitational valley powerful enough to bend the trajectories of hundreds of thousands of galaxies, including our own Milky Way, dragging us through the void at staggering velocities. Yet, when placed against the ultimate scale of the observable universe, even this colossal structure is profoundly humbling. The Great Attractor is but a single knot in a much grander tapestry. It is dwarfed by the sheer immensity of the Shapley Concentration, pushed by the vast emptiness of the Dipole Repeller, and ultimately outmatched by the relentless accelerating expansion driven by dark energy. Our cosmic river will never reach its destination. We are simply riding a temporary wave in a dynamic, ever-changing universe. This realization does not diminish the majesty of the Great Attractor. Rather, it elevates our own perspective. It is deeply awe-inspiring to consider that from a small, rocky planet orbiting an average star, a single species has developed the technology and the intellect to peer through impenetrable walls of cosmic dust, map the invisible rivers of dark matter, and comprehend the monumental forces shaping our celestial neighborhood. Thank you for joining us on this exploration of the cosmos. If you enjoyed this journey through the universe, please take a moment to like the video and subscribe to the channel for more deep dives into the unknown. Finally, we would love to hear from you. Please leave a comment letting us know from which part of the world and at what time you are watching this cosmic journey.